In 1960, physicists discovered that completely different materials can all behave identically near a phase transition. The details can vanish, and only a few numbers called critical exponents can govern their behavior. They called these universal relationships scaling laws. And 60 years later, the same kind of law showed up somewhere nobody ever expected: inside neural networks. Welcome back to this new episode. In our last video, if you remember, we discussed pre-training and data part of large language models. But today we are answering the $100 million question. How do these AI companies building foundation models know exactly how big to build their massive AI models without wasting fortunes on trial and error? And the answer is the scaling laws. When training a large language model, you basically have three knobs you can turn: the number of parameters that determines the model size, the amount of data, and the total compute power. Because these neural networks are chaotic engines full of billions of interacting weights and biases, in short, parameters, you would expect that turning these knobs would give you messy, unpredictable returns. But in 2020, researchers at OpenAI plotted a model's performance, its test loss, against its size, data, and compute on a log plot. What they observed was quite interesting. They got a perfectly straight line. It was a clean, predictable power law holding across 7 orders of magnitude. The returns diminish slightly over time, but they diminish in a perfectly predictable way. This means that you can literally extrapolate exactly how smart a model will be if you make it 100 times larger. In fact, OpenAI used this exact math to predict their advanced GPT models' final performance by running test models that used 10,000 times less compute. They knew exactly what they are going to get before they spent even a single dollar on the final massive training run. But if you ever taken a machine learning class, you're probably screaming at your screen right now, because classical machine learning is built on the bias variance trade-off. The textbook rule is a U-shaped curve. As you make the model larger, its error falls, it hits a sweet spot, and then it violently rises again as the model starts purely memorizing the training data. This is called overfitting. So when a large language model was built with, let's say, 175 billion parameters, classical theory said it should have trivially memorized the internet and completely failed to generalize. But the U-curve never appeared. Bigger models just kept getting better and better. So were the textbook wrong for 50 years? Well, actually no. They were just looking at the tiny corner of a much larger picture. Large language models avoid these overfitting for 3 brilliant reasons. Number 1, they barely glimpse the data. Overfitting happens when a model stares at the same example over and over. Modern large language model pre-training usually only goes through the massive data set once. You cannot memorize what you barely saw. Number 2, double descent. Researchers discovered that if you push a model's capacity past the point where it perfectly memorizes the data, crossing what is called the interpolation threshold, the test error actually falls again. Because massive models have so many parameters, gradient descent isn't forced to heavily confront the math to fit the data. It organically finds incredibly smooth, simple solutions. Number 3, a bottomless task. Predicting the next word on the internet isn't a simple math problem. It's an unbounded task requiring grammar, logic, coding, and reasoning. Even a 175 billion parameter model is technically under-parameterized for the complexity of human language. Here is where the industry got it wrong though. People thought scaling laws just meant make the model bigger and bigger. In 2020, early scaling laws suggested that if you had a bigger compute budget, you should mostly scale up your parameter count. This launched an arms race of purely gigantic models. Like for example, DeepMind's Gopher model, which had 280 billion parameters, but was only trained on 300 billion tokens. So in 2022, DeepMind published the Chinchilla paper, which corrected a subtle flaw in the original math. They proved that parameters and data tokens actually need to scale together, roughly 1-for-1. The optimal mathematical recipe for training is roughly 20 tokens of data for every model parameter. This proved that the giant 280 billion parameter model was dramatically undertrained. To prove it, DeepMind built Chinchilla, a model 4 times smaller than Gopher, at just 70 billion parameters, but trained on 1.4 trillion tokens. Using the exact same total compute budget, the smaller Chinchilla model crushed the giant Gopher model across the board. But wait, there's a real-world catch here. That 20-to-1 ratio is only optimal for the training phase. Once a company deploys a model to millions and millions of users, the inference cost, the compute required to generate the text every single day becomes the real bottleneck. To keep the inference cheap, companies intentionally overtrain smaller models, pushing the ratio to roughly 150 tokens per parameter. This is exactly why models like Meta's Llama are incredibly capable, but still very cheap enough to run on standard hardware. Scaling laws are the ultimate proof of the bitter lessons of AI. Human cleverness and handcraft code are always eventually beaten by simple architectures that scale massively with compute. But here's the fascinating part. While the model's loss improves on a perfectly smooth line, its actual capabilities do not. Specific skills like multi-step reasoning or translating real languages often sit at 0 and then suddenly emerge out at nowhere as the model crosses a specific scale. We get perfectly predictable loss, but we are constantly surprised by unpredictable gifts. And as we start running out of high-quality human text data, hitting the data wall, the new frontier of scaling law is shifting to inference compute, letting models think longer at runtime to unlock even deeper reasoning. So, if you found this deep dive valuable, please hit the subscribe button, because in our next episode, we are going to look at the brutal physical engineering required to actually process this math, the GPU memory wall. I will see you in my next video. Take care. Bye.